All right. Sorry about that. I lost internet connection for a second, but I was basically saying that these I hat and J hat, we're not going to use these for the kinematic equations. We will use these in vector related problems. Um, but like I said, they're just going to help us um when establishing direction, and you can see there how they're related. Here's an example of a problem where you might use but careful. This problem was created by the Tok Tok marker destroyer. Um, so I did not create this problem, and it was a very good problem, so I used it in this video. But it already has the answer shown, but we're going to just talk about how you would get that. So you can use those like I hat and J hat to write a vector representation. This might have been something you saw in your ACT or SAT or something. They throw those in there because, or like even if you didn't learn this, but it's not that hard to figure out. So what you do is the I direction is going to be X direction. So you're going to just go from the tail to tip. So this is the tail and that's the tip. So we'll say, all right, it's 1 and then to -3. That's going to be left 4. So -4i is what it is. And then it goes from -1 up to +1. So that's up 2. So plus 2j. That's really simple. So thank you, Talk Marker Destroyer. All right. Um, Now, you can also use this representation of vectors to add them. So we have the tip and tail method, right? But we can also just use this way. So you can see we did the tip to tail method as we learned, but look, we could have also just done this. 2 plus 3, 5, 5 plus 1, 6. So we can just add the I and J hat components. Hey, we can also do that for multiplying. So you can see if we want to get from 2a or sorry, just a to 3a, it's going to be okay, 2 times 3, 6. 1 times 3, 3. Pretty easy. All right. Here's a problem that we're going to look at it in a future video, but I just want to read it and talk about how we would or could solve it. But we're going to look in a future video, as I mentioned, with lots of problems, but including this one. So if we had a problem like this, ship A and B leave together from the same point. For 2 hours, ship A travels at 10 miles per hour in a direction 40 degrees west of north, while ship B travels 20 degrees east of north. What is the distance between them in 2 hours? So a problem like this, if we see something like that, 40 degrees west of north or something like that, that's angle, in case that isn't obvious. But you have to also think about the angle is, if we're saying west of north, that's going to be in reference to a y-axis, right? Because north and south, that's like y direction. So that means that, remember, that means instead of cosine being x and sine being y, it's other way around. Cosine y, sine x, because that angle is against a vertical line, and that is north. Um, so that's important to know for when you would solve this. And another thing that sticks out to me is I see um, miles per hour, and that's not what we like to do. So we would have to make that meters per second. Um, hey, and the reason why it's not really just for fun. If we use G in an equation, which we would not for this, but for other kinematic equations, G makes everything else have to be meters and seconds because of what G is. 9.8, that calculation is involving meters and seconds, so you can't use other units. So for this, you could use the law of cosines, which I don't really like it that much. It's kind of an annoying thing. But you could also use vector separation. So we will see how you could do that in a different video. All right, t tilted coordinate system. I already said this earlier in the video, is that sometimes it makes more sense to have our x direction as something that's tilted. So we could say this is the x direction instead of it being just flat. Um, and that makes sense for an inclined plane. Um, Two dimensions. So we've already looked at one dimension motion. So we're just going left to right, just going up and down. But it's possible to be going in two directions at once. So we're going right and up or something like that. And if that's the case, then if you're using kinematic equations, you'll have to use a different one if we're talking about X or Y. So you have to consider them separately. And you use these in AP Physics if you took that. And, ooh, sorry. Um, and the only thing that's the same that is not different for X or Y is time. So if you want to translate between the equations, like use one thing to find something in another, you can do that through time. And we'll see that when we do examples. But since those are the same thing, or the t is the same for both of them, then you can use that to find something in a different one, if that makes sense. Now, just keep in mind what is zero and can be canceled out in certain instances. So the top equations here, they look really long, but in some situations you can cancel out things. So like if something's launched horizontally, then this part would be zero because the initial y velocity is zero if something's launched horizontally. So that whole thing goes to zero because in zero times t, that's zero. So that whole part goes away. And another thing is that you can subtract this on the other side for both of these, and it can really just be delta x, delta y on the other side. Um, don't forget your squareds when you have them. And if you take the square root of something, it has a negative and a positive answer. Gotta be careful. And sometimes you can choose between one of those answers that makes sense for the problem. So, um, once again, we'll see this when we look at examples. And yeah, like I said, just be careful about if you're gonna have something be negative or positive. It will sometimes be due to the context of the problem. All right, we can talk about projectile motion. Projectile motion is going to be something that's shot or launched from a certain angle. And that launch angle, um, whatever it is, will determine height and how far it goes. 45-degree angle is where it will have the maximum range. That's something good to remember. Um, and once again, to find the components, since this angle is against a horizontal axis or the x-axis, cosine goes with x, sine goes with y. So the initial x component of the velocity is going to be the initial velocity times cosine of the angle, and initial velocity times sine of the angle for the y initial velocity. Acceleration in projectile motion will be the following. The x direction, 0. No acceleration. Y direction, g. Negative g, it's really, I should say, negative 9.8. And also, that's also that we're ignoring air resistance too. So here is an interesting question. So if you have a uh, two balls that are the same mass, they are one is the red one is dropped, the orange one is fired horizontally. Um, which one's going to hit the ground first? So the answer, it already shows it for some reason. It's not what I want it to be like, but it's going to actually be the same time. That might seem confusing. You might think, well, if one of them is launched horizontally, then wouldn't that mean it's going to take longer to go all the way down? But as it turns out, that it's not, because that the key thing about a problem like this, if you were asked it, is they're trying to make sure that you know that the X and Y direction are separate. So the distance that it's going is um for it falling is the y direction. So something that happens in the x direction is not going to affect the falling time. So not an x distance or x velocity. It will not change because these are independent of each other. All right, acceleration in two dimensions. So acceleration can be vector can be broken into components. Um, we could say uh par parallel component that's going to be associated with the change in speed. Um, and then the one that's perpendicular is associated with a change in direction. And we'll talk more about that later. Um, here's another question that's a little bit sneaky. So we have two projectiles. You can see they're launched at different angles. Which one's going to hit the ground first? One or two? Well, it's going to be two. And why is that? Well, the angle of number one is larger. Since that's the case, there's going to be a larger velocity. And if you don't believe that, well, to find that velocity, it's going to be the initial velocity times sine of the angle. And a higher angle, uh, or a higher sine of an angle means, oh, or like a higher angle is going to make this whole value, sine of the angle, larger. And when multiplied by this, it's going to be a larger value. So higher angle means higher velocity. And if that's the case, higher velocity, it can go up further. And then, I mean, that makes sense, right? It would be able to go up further if it's a larger angle. But then that also means that it has to come down too. And since it took longer to go up, it's going to take longer to go down. So that's why that one takes longer than projectile two. All right, if we're talking about relative motion, um, basically we're saying what is something's motion in uh relation or relative to a different uh thing or object. So if we're talking about in this situation, Bill in the car is going 15 meters per second. Um, to Amy, that's what it will look like because she's stationary. To Carlos, it's going to look like it's only going 10 meters per second because he already is going 5, so it's only going 10 faster than him. So it's going to seem like, from his point of view, only 10 meters per second. So for that, we would say um, the velocity of Bill relative to Carlos. So we could say Vx BC because the what we write it as is going to be, if it's AB, it's going to be velocity of A relative to B, or as seen by B. And in this case, it would be the velocity of Bill as seen by Carlos. So it would be uh, Vx BC. And then for Bill, Carlos, it's going to look like that he's going in the left direction 10 meters per second. And Amy, it's going to look like she's going negative 15. So in that case, you would subtract it. Does that make sense? All right, the last thing we're going to talk about is Galilean transformation of velocity. So this is just basically something where we can use vectors in this form to help calculate a different component. And you can see that equation right there. We'll apply it in some problems. So that's going to be it for this video. Thanks for watching.